Over the past couple of lectures, we've introduced the concepts of data abstractions, types, and aggregate structures. What we want to do today is spend some time pulling those pieces together to explore the idea of data abstraction in more detail. And in doing this, we're going to examine a couple of particular examples. But what we really want you to see is how in designing any data structure, in fact in any language, not just in Scheme, we have a trade-off. The trade-off is between concrete structures that are very efficient but prone to misuse versus abstract structures that nicely insulate the implementation from its use, but which may suffer from efficiency issues. This may sound a bit odd. A typical instinct, especially for a less experienced programmer, is to opt for efficiency. You want code that really motors, right? But in fact, if you're building parts of a big system that will involve use over extended periods of time, like years or decades, and that will involve components from a large number of users, then robustness, modularity, and ease of use are typically much more important than speed. So today we're going to do an initial exploration of this idea. We're going to examine three different kinds of data structures that move from concrete to abstract, culminating in the creation of a table data structure. We'll also see how design choices influence the implementation of an abstract data structure with different kinds of performance. And we'll see that the fundamental issue for designing abstract data types is using this methodology to hide information, both in the types and in the code. Okay, here's where we're headed. We would like to build an abstract data structure of a table. Now conceptually, a table is just a collection of bindings, and we're free to think about different ways of structuring that collection. And what's a binding? It's just a pairing of a key and a value. Or in other words, the key tells us the entry into the table, or how to find something in the table, and the value tells us the thing that's actually associated with that key. Now, we could define the behavior we want a table to have without having to consider the specifics of the implementation. So in particular, we want the following abstract interface between a user of a table and the table itself. First, we need a constructor for building the table. We'll just call that make. As we're saying, we're going to ignore for now the issues of how it's done. We can just use make as a user to say, give me a new table, and it will. We need a way of inserting something into a table, a binding into the table. We'll assume that such an insertion replaces any previous binding for that key. And also note that we don't say whether the old binding is actually physically removed from the table or whether the new binding simply shadows the old one. Why is this relevant? Well, notice that there's likely to be a trade-off here of efficiency in space, whether we keep the old bindings around, versus efficiency in time, how quickly we can add new bindings, and whether keeping old bindings around adversely affects our ability to recover bindings. So at this stage, all we said is that put will take a key and a value, create a new binding, put it into the table, and replace the previous binding some way so that we can't get at it. And of course, we need a way of getting things out of the table. So we'll have another abstract interface called get that takes as input a key, looks up the key in the table, and returns the corresponding value. Let's stress again, we've said nothing about how to implement this. From a user's perspective, this is all they need to know so long as the contracts for this data abstraction hold. And this, in fact, is a really important point. This definition of an interface to a table really does, in fact, define the abstract data type of a table. From the user's perspective, using these interface abstractions is sufficient to enable them to make use of a table and have it do the right thing. The details, the code we're about to show, will be an implementation of this abstract data type, but of course there can be alternative ones, and that's one of the points we want to look at. Nonetheless, this abstract interface really defines a contract between the insertion and retrieval of bindings in a table, as well as what kinds of things the table is going to hold. Before we get into the different kinds of data structures that will lead up to a table, let's first think about why they might be useful. An obvious place is in keeping track of things like personnel data. For example, suppose you've just started up a wonderful new .com company of some sort. One of the things you might want to do is have a database of the people who are going to be working for you. So you can keep that, obviously, in a table, just listed by or keyed by the names of the people that are your employees. Now, associated with each key in our table, where key here is the name of a person, an employee, we might have another table that lists information about that person, what their age is, what their job title is, how much they get paid. And of course, associated with that might be other information that also will be listed in tables. For example, pay structures over the last year or last few years. Not only do our table data abstractions need to be flexible enough to allow for other tables to be entries within the components of a table, as we've just seen, but we may have other ways of trying to gather information together in a table system. For example, we might have another table within our system that lists the ages of all the employees in the company. Certainly we can build a table where the keys are the ages of the employees. Here, however, the value associated with it might be something like a list, which we've obviously seen how to build, where the entries of the list point to entries in other tables that are the actual data structures of the people of that particular age. So we see that our tables need to be very flexible, and if they are, they can contain a lot of very valuable information that should be easy to manipulate. Let's start by looking at the idea of pairing keys and values. This is going to be the heart of a table implementation, and we want to see how different choices influence the way in which that table will behave. A traditional structure for doing this is called an A-list, or an association list. This is a list in which each element is itself a list of a key and a value. Or in other words, it's a list of lists, all of which are 2 elements long. So for example, if we want to represent this table, and notice this is an abstract definition, it's simply a binding of x and 15 and y and 20. If we want to represent this abstract table as an association list, we can represent it by this list of lists. Each of the inner lists is 2 elements long and contains the key and the value. Or to do this a little more concretely, we could represent this particular table with the following box and pointer structure, the following list of lists. And you can see the nice structure here in which each element of the top level list is a binding, and each of the bindings is just a list of the name and the value, just as the first and second element of a 2-element long list. If we were to make the design choice to use A-lists as our representation for a table, then we just need a couple of operations. First of all, we'll need to have a way of finding an entry for a key and returning the associated value. Okay, here's the definition for something that would do it. Let's call it find associate. Takes in a key and an A-list. And what's it do? Well, it basically walks down the A-list looking to see if the first element of that list has a key value that equals the key passed in. And note how it does it. We have the usual check to see if we've got an empty list, in which case we're going to return false, saying that the key is not in the list. Otherwise, we use equal to test whether the key is the same as, and oh, there's that funny car of something. So the first car gets out the first element of the A list, and the second car will get out the key. If those 2 things are equal, we will then return the value associated with that key. And if you go back and look at the data structure in the previous slide, you'll see that the kadar does the right thing. And of course, if this element isn't something that matches the key, we'll move on to the next portion of the A list and continue looking for the thing that does match. As an example, let's give a name to our little simple A list that we did previously. Call it A1. Notice the use of the quote in front of the list structure to get the list structure out exactly as we'd expect. We saw this a couple of lectures ago. Then, doing find ASOC on A1 with the key Y will return the value of 20. And you should trace through the code here to see why it does the right thing, particularly looking back at the blocks and pointer structure to see how it walks its way down the list looking for the right piece. Adding a new entry into this A list is pretty easy. We'll just const it on the front. All we have to do is take the key and the value that we want to associate together, glue them together, making a list out of them, since that's how we're putting them into the A list, and then just const that onto the front of the A list. Since the A list is itself a list, a const of something onto it will give us back a list, so this will have the right form. Note that in this implementation, we don't actually remove the old value from the list. We just shadow it with a new one. Why is that right? Well, given how we've implemented find ASOC, we're guaranteed to see only the most recent binding, the one at the front. And if that means anything that's further down will simply hang around as part of the list but never be accessible. Of course, you might think about what this does to the efficiency of find ASOC. For example, if we have to find a binding that was added early on, but where the list has had a lot of other things added to shadow that one, what will happen to the efficiency? Nonetheless, here's a nice little implementation. So for example, we can add a new binding to our old table, A1. We'll add an association of Y and 10 to that. We'll give it another name, call it A2. Notice we need to do this because we need to have a way of referring to the table. Now A2 has a list structure that is 3 2-element long lists, with our new binding of Y at the front and our old binding of Y still hanging around at the end. If we call find ASOC with the key Y on this new table, notice we'll return the value 10. And you ought to convince yourself of that by looking at the code from the previous slide. So this looks like a pretty nice little implementation, but let's think about this structure. In particular, this is not an abstract data type, and here's why. First of all, we have no constructor here. We're just building the list using list operations or quotes. This looks like a nice, quick way of doing things, but it has an important impact. In particular, there's no abstraction barrier here. That means that there's no way of separating out the implementation of an A-list and the manipulation of it from the use of the A-list. In fact, A-lists are designed that way. The definition in the scheme manual says an A-list is a list of pairs, each of which is called an association. The car of that association is called the key. So it's intended, in fact, to just be an exposed list. As a consequence, the implementation is exposed, meaning that the user can go in and operate on the A-list just using list operations. We could go in and do things like this. It looks nice and convenient, but in fact is a dangerous thing to do, and let's talk about that in the next slide. So why do we care? Why do we care that A-lists are not an abstract data type? There are a lot of reasons, but the primary one is because of modularity. This is something that's absolutely key to good software engineering and software design. We want to build a program that is created out of modules that we can glue together, that we can treat as black box abstractions and manipulate. The real reason we want that is because it will allow us to change one module without having to change any of the rest. And why does that matter here? Because A-lists have poor modularity. Since we have exposed the basic guts of the implementation to the outside, it means that other people could write programs that use operations like filter and map directly on the A-lists. There is no way of separating out the use of the table from the implementation of the table. If later on we decide to change the implementation of the table, we may be screwed, because these operations are assuming that A-lists are the basic implementation. They're assuming that they can do these kinds of operations directly onto the table. As a consequence, if you decide to create a different table structure, you're going to have to go through and change every piece of code that manipulates. And how do we do this? Well, basically we're going to hide information. To get good modularity, we're going to hide details. In particular, we'll hide the fact that the table is implemented as a list. We'll separate that out from the use of the table. This has two parts. The first part is that we'll create new kinds of abstractions to get at the parts of the table, new constructors and selectors, and we'll insist that in fact anything outside of the internal implementation, any other part of the program, cannot use list operations, but has to use those abstract interfaces. This is exactly what abstract data types are about. They're techniques for allowing us to create clean interfaces between the internals of an abstraction and the use of the abstraction, and we want to be disciplined in how we enforce this. So let's build on this idea. We know that we should be able to use A-lists to represent the internal structure of the table, but we need to do this hiding of information, this separation between the internals of the table and the outside world. And here's how we'll do it. First, we'll need a constructor, makeTable. We'll call it makeTable1 because we're going to do different versions of this. And this will simply put a tag on front of a table structure. And we've given a definition of table1 tag to be the quoted symbol table1 just to give us something. Now, we can create a get operation on a table by saying, given a table, remove the tag, get the actual table implementation, and then use find ASOC to look up the key in that table. So we're using a representation of an A-list as the internal part of the table. To put something new in the table, we can again get everything but the tag on the table, that is the A-list, and use add ASOC, as we did before, to put a new key and value into that list. That will return for us a new list, a list with that binding added to it. The only other thing we have to do is put the label back onto the table, and we can do that using an unusual operation that we're going to come back to in a few lectures. This new operation setCouldr you can think of as taking the box and pointer structure pointed to by the argument or the value of TBL, finding the coulr of that pair, and changing that pointer to point to this new structure, to this new list. We're not going to worry too much about this new operation. We simply want to take note of the fact that we can add a new table or a new association list to the tag and return that as the value of the whole thing. So let's see how this works. If you need to, flip back to the previous slide to check out the code as we go along. First, let's create a table. We'll define tag table1 or TT1 to be the new table we get by using the constructor. Here's what that looks like. TT1 points to a list structure. The car of that list is the symbol table1. That was our tag that we put in there. And the coulr is just the empty list. We don't have anything in that A list yet. Now, let's put a new pairing or a new binding of a key and a value into our table. So let's put the binding of y and 20 into our table. So what happens? Well, table put uses add ASOC. It gets out everything but the tag type, that is the empty list, and it creates a new binding of the symbol y and the value 20 as an association list and constants that onto the front of it, creating this structure. And then we use this new operation to take the box pointed to by TT1 and mutate or change its coulr to point to this new structure. Notice what we have now. We have a new table, it has a tag on the front, and it has an A list at the back that has one binding in it. Now, let's add another thing to our table. Let's put the binding for x and 15 into the same table. Again, if you look back at the code, you can see what this does. Add ASOC first takes the table part of the table, that is, removes the tag and gets that structure pointed to by in blue. It then creates a new binding, a pairing of x and 15 as a to-list, and conses that onto the front of this new structure, as shown here in red. This new structure is our new A-list, and it has in it 2 bindings. And then we once more use that setCoulter operation to take the thing pointed to by TT1 and change its coulter to point to this new value, removing the old binding. So we now have a new A-list associated with this table. If we get a value out of the table, that is, we get the pairing associated with the binding of y from this table, table get does a very similar thing. In particular, it removes the tag, gets the pointer to the A-list, and then uses find ASOC on that A-list to find the value associated with this key and return that value, just like before. So now we have a nice little implementation of a table, with a tag out front with some constructors and selectors associated with that table, and using inside of this table an A-list to actually do the representation of bindings of keys and values. Now, what is it that makes table 1 an abstract data type? First, it has a type tag. Well, that's careful programming, but that alone is not enough to turn it into an ADT. What else? It has a constructor. Again, having a separate interface is a help, but that's not sufficient. And it also has accessors or selectors and mutators, that setCoulter thing. Is that what makes it happen? Well, again, that's not enough. After all, A-lists have this opportunity as well. In fact, the key issue is the isolation of the abstraction from its users. We don't use any list processors like car, coulter, map, or filter on the tables. And in fact, we can't because the type of the object passed back by accessing a table is wrong and won't work for such procedures. What we have done is actually hide the implementation of the guts of a table from the users of tables. This abstraction barrier allows us to freely change our implementation without affecting anything written by a consumer of tables. And that's the key. We've hidden away the A-list from everything else. We could change that, and nothing should have to change on the outside. This is a key point, and one worth generalizing. By creating a distinct data structure type for tables, we have in essence hidden information behind a name. We've made that name opaque to the user. What do we mean by this? Well, it says that by creating a new type in this way, its name hides the details. For example, suppose I give you a new data type and simply tell you that it exists, but not anything about its details. Let's call it my type. Further, let's suppose we have 2 procedures with the following type contracts. M1 takes a number as input and creates for us a new thing of this type, my type, and M2 takes in one of these things of my type and does something to it. Given just that information, we can ask the following questions. Which of these 2 expressions is actually acceptable, and which one is not? Well, clearly the first is fine, and let's see why. The type of object returned by M1 is the type expected by M2. We don't know anything about that type, but the contract, the opaqueness of the name, allows us to separate that out, and we're guaranteed to be able to do the right thing here. On the other hand, the second expression should bomb out, because here the type of object returned by M1 is not appropriate for a procedure like car. We don't know that the thing coming back is actually a pair, and we should not be able to assume that. In essence, the opaque name and the infrastructure hidden behind it, meaning the data abstraction that isolates the accessors that can use the object from the details that implement it, this opaque name has guaranteed clean behavior for this particular data type. And as a consequence, this means we can change those representations without affecting anything that's on the other side of that opaque name. So for tables, here's everything that a user needs to know. First, we have this opaque type, this thing called a table 1, that has inside of it 2 arguments of types k and v. Or said another way, table 1, using this notation, is constructed out of pairings of k's and v's, but we haven't said anything about how. Our constructor for this type takes no argument as input and gives us back one of these data types, a table 1, where the elements that are paired together within it can be of any type. Our constructor, table put, takes one of these abstract types plus a k and a v, and it doesn't give us back anything because it's just doing something to the structure itself. And our accessor, table get, takes in one of these abstract types plus a k and either gives us back the v associated with it or the empty list. Note again, this is everything that the programmer or the user needs to know, and nothing is said here about A-lists or conses or cars or anything else. It simply defines an interaction between one of these abstract data types, a table, and the elements within it. Hiding below that abstraction barrier, hiding behind that opaque name, is the actual implementation. Here we've made a choice. In particular, we've said that the implementation for this abstract data type of a table is a symbol, identifying the kind of table, glued together with an association list, an A list, whose elements are pairings of K's and V's. And what's an A list? Well, we've seen it's just a list of lists, a list of pairings of K and V and null. So that internal representation of K cross V cross null says it's a list of K and a V, and the overall list is simply a collection of all of those things glued together. This is our particular choice right now for how to build a table, but this is hidden from the user. So here are the key messages so far. First, we've seen that we can use this association list structure to represent the internals of a table, but we also have seen that we need to separate it out, and the data abstraction technique allows us to use that representation while hiding that information. In general, this is going to be an important point, using the notion of constructors and accessors to support information hiding, burying the details from what is actually seen by the user. That's essential, as we've said, to building modular systems, which is absolutely essential for good software design. Now, let's look at how the data abstraction allows us to alter the internal implementation of the table without affecting anything that consumes tables. That's been our point all along. To motivate this, suppose we build a table and monitor its usage. And further, suppose we find that a lot of time is spent in the get operation. In other words, most of the time, as you might expect, is spent retrieving information from the table rather than actually adding to the table. If that's the case, it would be really nice if we could come up with a faster implementation of the get operation while preserving all of the contracts associated with the table itself. In fact, there's a standard data structure for fast table lookup called a hash table. And indeed, you'll see a lot more about things like hash tables in courses like 6046. For us, it's simply enough to say that the idea behind a hash table is to keep a bunch of association lists rather than one, and to choose which association list to use based on a function called a hash function. What that function does is take the key, the thing we're searching for in the table, and compute a number between 0 and the number of lists we have. That will tell us which list to look in, and only in that list will we then go and try and find the key. You can already see why this should be faster. Rather than having to search one real big table to find a key, if we can make the hash function fast enough, we can cut this down into searching a much smaller table structure to try and find the key. By the way, you'll find when you take 6004 that this idea is regularly used by computer designers to support fast memory access in what are known as caches. For our purposes, we want to look at the idea of a hash table as a way of building a much more efficient abstract data type for a table. So what does a hash function look like? Well, it simply needs to be a function or procedure that takes as input a key, as we said, and computes a number between 0 and some defined range. And it should always do the same thing for that key, so that we always look in the right place for the thing associated with the key. As an example, suppose we have a table where the keys are points, that is, xy coordinates of points in the plane. For example, points that are going to be on a graphic display of some sort. And associated with each point will be some graphical object. That point's part of a particular structure, like a circle of radius 4 or a square of size 8. For example, if my little graphic system includes some simulations and I'm about to move one object in that screen, I'd like to know which points are covered by that object. And this means a nice way to do that is to take a point, be able to look up the objects that cover that point, and then do the appropriate manipulation to decide which points should be re-rendered and which points can be left alone. For us, the question is, how do I create a hash function that would take points as input and compute a number between 0 and 1? So for our purposes, the real question is, how do we build a hash function? And here's a simple one for this little example. Given a point and a number n, we'll take the x and y coordinates of that point. Notice we're assuming some data abstraction to get them out. Add those two numbers together, and then return that value modulo n. And modulo means we take the remainder of that number divided by n. So we're guaranteed to get a number between 0 and n minus 1. You might already realize that a good hash function should be something that uniformly distributes the keys among its possible output answers, or as uniformly as it can. And that's often an issue for interesting design choices. Here, given that we assume points are randomly distributed in the plane, this function will do a pretty good job of giving us a roughly equal distribution of keys and values of the hash function. So a hash function basically chooses a bucket into which to put an object or from which to search for objects. The idea is that given a key, we first apply the hash function, which computes an index, that is a value between 0 and n minus 1. That index then tells us which set of things to look in, which bucket, as I said earlier, to look in order to find the object we're interested in. And as we said, if the hash function is reasonably well behaved, this means that on average we're only going to be doing 1 over n the amount of search for a get operation that we did in the straightforward implementation. And as long as the hash function is efficient, we should get a big net benefit out of this idea. Note that we haven't said anything about how those buckets are glued together. This kind of looks like a list, but we don't have to do it in a list, and in fact in a second we'll see that we won't. The main idea here is that if a key is in the table, then it is going to be in the association list of the bucket whose index is given by the hash function applied to that key. Okay, now to build a hash table, and actually implement a hash table, we need an efficient way of gathering the buckets together. We're still going to represent each bucket as an association list, but since we have an ordered sequence of buckets, we'd like an efficient way of representing them. For this, we'll introduce another common abstract data type, a vector. This is a fixed size collection where access is determined by an index, a number. It's a little like a list, but with 2 important exceptions. First, the size or length of the vector is fixed at construction time. And secondly, given an index into the vector, we can retrieve the contents of that location in constant time. Whereas, as you remember with a list, it would take linear time to walk down to that point in the list. With that idea in mind, here's the contract for this data abstraction. As before, the type is opaque in order to hide the details. And in fact, the elements of the type are just going to be some arbitrary type A. We're not going to worry about that. And we're not going to worry that much about the implementation of vector. We're going to treat it as an abstract data type. Associated with this data abstraction is a constructor, make vector, and 2 operations, vector ref that gets out an element from the vector, and vector set that goes in and changes an element of a vector. Examples of the kinds of operations we'd expect to see are shown at the bottom of the slide. We can create a vector with a size number of locations, each of which initially contains some value that we specified. We can get back whatever is stored at a particular index of the vector, and we can certainly go in and change what's stored at an index of a vector. And of course we have to be careful about making sure we don't try and go beyond the end of the vector. This then gives us a hash table, a new data type. We've built an implementation of it on top of another kind of data type. We can just assume it does the right thing. That's part of our goal of abstract data types. And we've seen that this hash table should have a different kind of behavior in terms of how it retrieves and stores things. What we want to now turn to is how to use the idea of a hash table to change our implementation of an overall table. Given our abstract data type of a hash table, in fact we've built one, but given that abstraction, let's go back and see how we can use it to change the implementation for our top level table. Our goal is to see how we can replace the implementation, change the efficiency of the operations, but not change anything that is using those tables, so that a programmer using a table doesn't see any of this. The main change is in how we construct a table. As before, we'll have a tag, but now when we construct a table, we'll specify 2 things. The hash function we're going to use within the implementation, and how big a hash function we want to have. That is, how many buckets we want to break our representation down into. Notice what we do. We list together the tag, the size, the hash function, and the actual buckets, that is, the vector that represents the places where we're going to store everything. And of course, associated with this, we'll have some selectors to get back out the pieces of the table. Something to think about, by the way, is for each function on this slide, what kind of beast is it? A constructor, an accessor, or an operation, or maybe none of the above? So with this change, how do we do gets in this table? Well, we're still going to have the same inputs, a table and a key. Here, we're going to get the hash function out of the table. Notice the selector pulling it out. And we're going to apply that to the key and the size of the argument. Notice the selector to get that out of the table. That will tell us which of the buckets to look in. We'll call it index with that temporary binding using the let. And then, just as before, we use our association list to find that key in the right spot. And what's the right spot? We use the index and the buckets of the table to find the right association list, and vector ref will give us back exactly that list. This seems like a lot of code, but stop and look at it. If you do, you'll realize that we're simply using the selectors and constructors, but in particular the selectors of our data abstractions to pull out the right pieces of the table and find, therefore, the right thing inside of it. Also notice, this function has exactly the same type as our original get. And that's important. It means that somebody using this can rely on it doing the right thing and not have to make any changes just because we've changed the internal implementation. To put something into this table, we do basically the same thing. Notice again, the type is going to be exactly the same as the original put. A table, a key, and a value. Here, we once more get the hash function associated with the table using that selector, apply it to the key and the size. That tells us which bucket to look in. We then pull out the buckets of that table and use our new abstraction of vectors to try and pull out the right piece. Having found that, we go in and change the association using our association list manipulation, and once more using the selector to pull out the right piece. And as we noted earlier, while it looks like a lot of changes, just walk your way through the code to realize how the selectors are simply getting the new association list out of the right bucket of the vector and doing the right thing with it. So let's look at a little example to see how the behavior has changed in terms of efficiency, but not in terms of view from the user. Let's define a new little table using our constructor. Notice again it has to take in both a size and a hash function. We'll use that hash point we had before. And here's a representation of the structure we get. TT2 for tagged table 2 points to a list. The first element of which is the symbol, the tag saying what kind of thing it is. The second of which is the size of the hash function. The third of which is the actual procedure itself. And we're just going to represent that as this double bubble for reasons we'll see in a few weeks. And finally, the last part of this is a pointer to a vector. And because the size is 4, this vector has 4 slots in it. That's what the structure looks like. So now, let's manipulate this table. Let's put into this table one of those points with an association paired with it. If you look back at the code, you'll see that this operation does the following. First, it gets the hash function and the size and applies that to this key, make point, in order to determine which part of the vector to look in. Having found that right part of the vector, it takes the association list stored there and glues on front of that association list a new pairing of the point and the value, as shown here. As we've been saying, this should be much more efficient since we're only looking into one of 4 association lists to do this work. Let's do the same thing with another association of putting something into the table. And in exactly the same way, this will create a new association list hanging off of one of the buckets of the vector, as before. Now remember, our reason for making this change was that we wanted a table that was much more efficient in terms of getting things out. So let's see what happens if we now try and do a get from this table of one of the things that we believe is stored somewhere in that table. If you look back at the code, you'll see that get for this kind of table does the following. It takes the key, that point structure, it takes out the size and the hash function that are part of the table, and applies those to this key to determine which vector to look in. In our case, we know that that should be the third bucket of the vector. It then goes straight to that bucket, pulls out that association list, and then uses normal A-list operations to find the pairing and return the appropriate value associated with that pairing. The key thing to notice here is that it's searching a much smaller A-list. In fact, as we expected, we should do only 1/4 of the amount of work we would have done in the normal case. The second key thing to note is that from the point of view of the user, this is all invisible. So what have we done? We've built an abstract data type, a table, a way of collecting information together. And we've then built 2 different implementations of the table, with the key idea being that the user of a table will not in principle see any difference. That is, the type contracts between the constructors and selectors of the table are identical. At the same time, we said one reason for doing it was to try and create a more efficient implementation of the table. So which is better? Well, I've kind of led you down a garden path because I suggested earlier that table 2 would be much better. But in fact, the answer is that it depends. It depends on what use you want to make of it. For example, table 1 has an extremely fast constructor and an extremely fast put operation. But its get operation is order n, where n is the number of calls to put. And you can see that because you know that it in principle is going to have to look down a long association list to find the right thing. Table 2, on the other hand, trades things off differently. First of all, its constructor is going to use up more space. It's going to have to use up enough space as determined by its input argument. Its put operation is going to have to compute a hash function. And that, we of course know, may be slow or fast depending on how clever we can be about designing the hash function. The get operation again has to compute the hash function, plus it has to do order n operations, where this n in principle should be smaller. It'll be the average length of a bucket rather than the total length of the association list. What this says then is that table 1 will be better if we're doing very few gets or if the table's very small. Table 2 will typically be better, but we have to be sure that we can both predict the size of what we're going to need and pick a good hash function that spreads things out evenly among all of the buckets. So why did we do all of this? Well, basically several reasons. We wanted to show you a new data structure, but more importantly, we wanted to show you how we can separate out the use of the data structure from the actual implementation. And we've used 2 different ideas here to show that. And indeed, the goal of the abstract data type methodology is to hide information, to use opaque names to distinguish between the operations we want to use on that data type and the internal definitions that actually make the data type go. And that's the lesson we hope you take away from this particular lecture.